Okay, welcome back to the second part of lecture 17. In the first part, we established, a spatial, dependence specification in our regression model. And then we came to a point where we wanted to evaluate the impact of this spatial dependence as specified through the variance covariance structure of the error model on the least squares estimators, right? So we figured that the least squares estimators, looked like what we see on your screen here. So we were working on a model of housing prices, and we are modeling those as, as a function of observed data on the spaciousness of a house, at a given location Sn, right? Which we index by the number of rooms, right? But we really want to understand what's the, how spacious is this property about which we are trying to understand the pricing. Okay, so we figured that we will get an estimate of this coefficient beta 2 based on the least squares algorithm, which is beta hat 2 least squares ls, which is equal to the covariance between P and R divided by the variance of R. We also figured that this beta hat 2 OLS is also a random variable by itself, and so what we also have to report is its precision, its precision metric, which is the variance of beta hat 2 ls, right? What we also know from our previous lecture, that is lecture 16, is that under the classical assumptions, a least squares estimator is blue. When I say it's blue, I basically want to say that it's the best linear unbiased estimator. Okay, now these are the properties of this beta hat 2 ls under the assumptions A1 to A6, but we know that A3 is violated under spatial dependence of model errors, correct? So now how do we go about evaluating these properties? Well, beta 2 hat OLS or ls is going to be still an estimator. It will not be a non-estimator just because there is spatial dependence. It's still an estimator. It is also still a linear estimator. Remember, it is linear in P. So if the coefficient parameter is linear in P, which is it's linear in P, that means that it is still a linear estimator, right? The question really now will arise is that, is this estimator unbiased and is it best? Is it a best estimator? So we understand what unbiased means. So basically what we are asking is, how does expectation of beta 2 hat ls given the data on R compare with the true value beta 2? And second, best means that this estimator is the one which will have the minimum variance among all the estimators of beta 2, right? Now we have to evaluate whether or not both these properties hold when A3 falls apart. Okay, so let's go out and evaluate whether or not the two properties best and unbiased still stay afloat when we introduce spatial dependence in the model errors, that is, we relax assumption A3. Okay, so let's do that. Okay, so what we are saying is, we are asking, is beta hat 2 ls unbiased when delta Sn, or let's say, I don't want to complicate the notation, when deltas, that is the model errors, exhibit spatial dependence. This is the question. So what we have basically asked is that, does expectation of beta 2 hat 2 ls given the data R on R equal to beta 2, where beta 2 is true value, which is the population model, right? It's the truth that we are after. We don't ever observe the truth, but we are still able to sort of figure out whether or not these things what we have gotten from a data driven estimate is close enough or not to the truth. Okay. So I'm going to write down, work with the LHS. Obviously, I have to, right? I have to work with the LHS. So I have expectation of beta hat 2 LS given R, which is to say that I am working with an expectation of, so just to make my notation easier, I'm going to just say expectation conditional on R is E sub R. This basically means I'm working with conditional expectations. In conditional expectation, R becomes the constant, right? So we are going to treat R as a constant value when we apply this expectation operator onto, the formulation that we are going to just write right now. N equals 1 to N P Sn minus P bar times R minus R bar. Remember, everything that is R, it is Rsn or R bar, they are both constants with respect to this expectation operator. R bar the whole squared. Now, we know that this Psn through my regression model, it is beta 1 plus beta 2 Rsn plus delta Sn. So the only thing that is random inside the expectation operator is going to be indeed the delta, because R is constant because we are looking at conditional expectation. Beta 0 and beta 1, they are both constants. They are just true values of these parameters. They are constant values, right? So the only thing to look out for is, is delta Sn. So I'm going to just say that, you can write down, you can do the mathematical manipulation, and you can show that this, expectation, the stuff inside the expectation operator will reduce to the following. So we will have expectation beta 2 hat LS is equal to beta 2 plus summation N equals 1 to N expectation R Sn times delta Sn divided by N equals 1 to N R Sn times minus R bar the whole squared. So what is interesting now to us is this expectation of the product of my explanatory variable R and the error term delta, right? This term is nothing but a representation of the covariance between R Sn and delta Sn. And this covariance is nothing but a representation of the expectation of delta given R, right, which is 0 by the second assumption, right? So the second assumption suggested the conditional expectation of errors, conditional on the x, which is, right, when I say conditional expectation, it is equal to 0. So A2 is not relaxed, A3 is relaxed, right? So when I say A2, I would always say refer to lecture 16, okay? So lecture 16, as you can see, is very, very important. It's very critical, right? So what will happen is that this second term will vanish, right? So that means this second term will vanish and I am left with beta 2. So expectation of beta hat 2 LS given the data on R is just the true value beta 2. That means, very, very important, that the least squares estimator is of, estimator is unbiased in the presence of spatial dependence in model errors, right? Specifically, I am only relaxing A3, okay? So, we will see that, it can have more complicated, implications, but for now, so far as spatial dependence is concerned, we are only relaxing A3. So even when A3 is relaxed, beta hat 2 LS is unbiased. It is a good guess of the true beta 2 value. Okay, so and by extension, this will mean, sorry, I'll use a different pen here. This will imply that beta 1 hat ls, which is nothing but p bar minus beta 2 hat ls times r bar, is also unbiased. So the regression estimators are unbiased in the presence of spatial dependence. This is a form of heteroscedasticity in data. So we said that A3 ensures homoscedastic errors, right? So we are working with a form of heteroscedastic errors. Again, you should go back and read Woolridge's book if you have not heard of this term before. Although I believe that having a more general variance covariance matrix, meaning that it's heteroscedastic and non-homoscedastic, non-spherical errors is a sufficient explanation. But if for details, please refer to Woolridge's book. Right? So we have this very important result that even when we have this spatial dependence going on, least squares, which is seemingly simplistic, does a very good job. I mean, I have a very good guess of the point estimate. My point estimate is a very good guess of what's happening in the reality. Okay, so going back and saying, okay, I have figured that I am also going to have unbiasedness so far as the presence of spatial dependence is concerned, which relaxes assumption A3. So as a next step, we are going to now ask whether we are going to ask, is beta hat 2 ls the best? When I say best, I mean minimum variance, right? The best estimator of beta 2 in the presence, or let's just simplify this and say when covariance delta u delta v is non-zero for every, or for some, not every, for some locations, location pairs u not equal to v. Right? So some pairs of locations which are separated by a distance, or let's say a lag, a spatial lag, we have, do we still have a best estimator? So now for that, we have to worry about beta hat 2 OLS. So I'm going to look at the variance of beta hat 2 least squares given data on R, which I am now going to define as VR, just for concise notation, beta hat ls, which is equal to the variance of R, not variance of R, variance conditional variance operator onto I equals 1 to n. So I'm just going to write the formulation of beta hat 2. So this is going to be P Sn minus P bar R Sn minus R bar divided by summation I equals 1 to n R Sn minus R bar the whole squared. Right? This can be then shown to be equal to summation n equals 1 to n R Sn minus R bar times Psn divided by summation n equals 1 to n Rsn minus R bar the squared. Okay. Now, I have said that I am taking this variance conditional on R. So that means R is a constant. So the denominator will directly come out, right? It's a constant. So when a constant comes out of a variance operator, it comes out as a whole squared. So it's going to come out as 1 over summation n equals 1 to n Rsn minus R bar whole the thing squared variance of summation I equals, oh sorry, not I, just a second, n equals 1 to capital N, R S N minus R whole thing times P S N. Okay, so it's all in the denominator. Now, we had said, like just like in case of unbiasedness, when we were evaluating it, we will substitute PSN with beta 1 plus beta 2 R plus the error delta. Okay, and then you can show, of course, you will be able to show that VR is equal to, so this is equal to 1 over, sorry about that, I have 1 over summation n equals 1 to n r minus r bar the squared whole squared variance of, now r is a constant, so you know as we multiply, you know, r minus r bar with beta 1, beta 2 r, we are basically working with constants, and the variance of constants is 0. So the only thing that is going to remain inside the variance operator is the random variable term delta. So I'm going to work with 1 to n r minus r bar times delta Sn. Okay. So as case 1, I'm going to work with the assumption A3 holds. That is, there is no covariance between, you know, the error term at different locations. So now if I were to focus, if you were to just, you know, bring your focus to this variance term, right? Of course, it's variance conditional on R. So R is a constant. But now evaluate it, you know, a little bit, you know, closely. So I've written variance of R with a constant. So I'm going to just replace this by a constant A, of course an, but it's a constant, and this by a random variable delta n, just to sort of make the notation easier. So summation n equals 1 to n a n delta n. Now this variance, if capital N were just 2, you would write as the following. You would write this as an squared variance of delta, sorry, a1 squared, right? So I'm going to work with it for a case when n equals 2. This will be a1 squared variance of delta 1 plus a2 squared variance of delta 2 plus 2a1 a2 covariance of delta 1 and delta 2, right? This is for the case when we had n, capital N equal to, right? We are very well aware of how the variance operator works for that simplistic case. Now, extend that understanding to the general case when we have more than 2, you know, variables, random variables being summed inside a variance operator. Okay, so my random variables are delta S1, delta S2, delta S3, all the way through delta Sn. So this variance in the general form, when we have, you know, homoscedastic or spherical errors, all the covariance terms are going to vanish to 0. So all I'm going to remain with is the term with the variance, and standing outside is the coefficient vector, which is squared. So I'm going to use this to write down the variance of beta 2 hat ls given our, you know, when A3 holds. Okay, so I'm going to do that now. So when A3 holds, variance of conditional variance of beta 2 hat ls is going to be 1 over summation n equals 1 to capital N r minus r bar the whole squared and the whole thing squared times summation, I'm going to apply my understanding of how the variance operator works when the covariance terms are 0. So n equals 1 to n r Sn minus r bar squared, and then apply the variance operator on each of the delta n's, okay, or the delta Sn's, sorry about the Sn, okay. And this variance of delta Sn, this value is nothing but equal to sigma squared. It's a constant. So the constant will directly come out of this will come out of the summation term. So I have 1 over summation n equals 1 to n r minus r bar squared, whole thing squared, times sigma squared times n equals 1 to n r minus r bar, the whole thing squared. And hence I can cancel one of the denominators, terms with what's sitting in the numerator about summation r minus r bar squared. Okay, so that's why the variance of beta 2 hat OLS will come out to be sigma squared divided by summation n equals 1 to n r minus r bar, the whole squared. Okay, now it starts to make, starts to appear, if A3 were to be violated, or if A3 does not hold, or it fails, where will the difference apply? Well, the difference will apply in the case that this covariance terms will no longer be 0 if A3 is violated. So that is something we are going to look at as the next case. So let's say case 2, when A3 fails, right? And we are talking about a very specific structure that we have, that we have articulated, in the variance covariance matrix. That is to say that, with the given structure, given the variance covariance matrix of model errors, that is to say that covariance of delta, u, delta v, right? And let's say if we were to, evaluate it for all the locations in u being S1 till Sn and v being locations S1 till Sn, right? So these are variable. We know that we can write this, we can define this as a n by n matrix, because you will have n factors of the row where u is varying, given a value of v, and for each given value of u or location of u, we can vary the v locations from S1 to Sn, right? This omega matrix for the given structure will be written as follows. When u equals v, we have the covariance given as, let's actually write it down, that we have this as sigma squared rho u minus v. Okay, so when u equals v, which is a diagonal elements, I have sigma squared all the way sigma squared. Okay, when I move from location 1 S1, when I move from location S1 on to location S2, I have my variance changes to sigma squared rho. When I move on to S3, my covariance will become sigma squared rho squared all the way till sigma squared rho n minus 1. Okay. Similarly, when I'm looking at the second S2, location S2 in the row, and I move across columns, S1 will have sigma squared rho, that's u minus v is just 1. Here I have on S3 also I will have sigma squared rho, because 2 minus 3 is also equal to 1, and all the way till sigma squared rho n minus 2. So I can keep going. The first term here will be sigma squared rho n minus 1, which is the difference between n, capital N, so it will be capital N and location 1, and you will have, okay, I have capital N's everywhere. Okay, so okay, I hope this is clear. Sigma square rho n minus 2, keep going, sigma square rho, and so on and so forth. Right? So now the off diagonal elements are non-zero. This is a specific form of heteroscedasticity. A specific form of heteroscedasticity that we have introduced through spatial dependence. Okay, so now if the covariance terms are non-zero, let us specify the variance of beta 2 hat again. So we are going to specify this for, for this case, right? So we are going to, I'm going to just write it down again. So I have variance of beta 2 hat least squares is given as 1 over summation n equals 1 to n r minus r bar the whole squared, the whole thing squared, and then variance of r summation n equals 1 to n r minus r bar times delta Sn. Okay, I'm going to write this as following. I'm going to generalize it. We have seen this form before. Okay, you have seen this form before in one of the earlier lectures. I'm going to write down this as summation n equals 1 to n and summation m equals 1 to n, right? So I'm moving u's and v's one by one. I'm going to write it as r Sn minus r bar r Sm minus r bar times the covariance of delta Sn comma delta Sm. Okay, so this is the most general form of the variance covariance, the variance of beta 2 hat OLS. And very clearly you will start, of course, these covariance terms will be directly sourced from the omega matrix, which is my n by n matrix of the variance and covariance factors, right? But what happens is that this is no longer equal to the minimum variance form, which is n equals 1 to n r minus r bar the whole squared. So we no longer have minimum variance in case of spatial dependence in model errors. Right? So the final implication is that the least squares estimators are not best, right? So they are no longer best under spatial dependence. So this is the implication that I no longer have a a very precise estimator. So least squares is still unbiased, but it is not so precise, right? So this is the implication that we have drawn from from when we introduce spatial dependence to the regression model, right? So as a next step, right, first we are going to just say that hence we are going to state formally that least squares estimators are not efficient in the presence of spatial dependence, right, in model errors, right? And now this spatial dependence in model errors, as we have seen, as we have stated earlier, is a form of heteroscedasticity, right? So that means that LS are not blue, right? And remember, they are still linear, they are still unbiased, they are still an estimator, but the trouble is they are no longer best. That is why they are not, a blue estimator. Now, what I'm going to do next is I'm going to state that the efficient estimators under heteroscedastic errors in general are called as the generalized least squares estimators, or better known as the GLS estimators. Okay. Now, so basically we have moved from a specialized homoscedastic, homoscedastic variance covariance structure to a more general, variance covariance structure where the off diagonal elements are not zero. And as a consequence, the efficiency property is taken away from the least squares, the ordinary least squares estimator, but they are then restored if we work with what are called as the generalized least squares estimators. Okay, so in the next part of this lecture, what I'm going to do is I'm going to formally introduce the GLS estimators, and then I'm going to provide you a general strategy for estimating such estimators, to getting to such coefficient estimators when you have spatial dependence of a general form in the data. All right. So see you in the next part of the lecture. Thank you for your attention.